Finally, now we prove that 3 implies 1. For this, we need to again review the relationship between the norm group, this norm group, and the Brauer group. Remember that we had a computation of cohomology of cyclic group. In particular, for cohomology in even degree of cyclic group, we have this formula here. So if F over L is cyclic, then because the Brauer group of F over L is could be written cohomologically as H2, right? We have the following description. Here L star is just the subgroup of F star fixed by the Galois group. So this allows us to interpret 3. 3, what does 3 say? 3 says that this norm is surjective for every cyclic extension of degree P, right? So that means that every element in L star is a norm, so 3 implies that this quotient is 0. Thus, 3 implies that for every cyclic extension F over L of degree P, both containing K, this cohomology group H2 is 0. So that's what we have. We have this, and what we want to show is this. But this group here, this group is not even, it's not cyclic of degree P, it's not even finite. So we want to somehow transform this to cyclic groups of degree P. But in the first step, we'll be less ambitious. We want to relate this with some group of pth power order. So here we want to use a claim that we proved before, which is that the pth cohomological dimension of a group is equal to the pth cohomology dimension of its pro-P CELO subgroup. So we bring this now to the computation of the cohomological dimension of the pro-P CELO subgroup. We'll call this the pro-P CELO subgroup of the absolute Galois group instead. But then remember, when talking about the cohomological dimension of pro-P group, we have proven that in this case it suffices. We don't need to check this for every A module. We only need to check this for Z mod PZ. So now we have changed what we need to prove into this statement. That's some progress because we have a finite group now, and this group is actually a P power. It's getting closer and closer to the form in the hypothesis. Now to get it closer to the form in the hypothesis, we want to relate this with some relative Brauer group. But first, let's relate it to some Brauer group. Observe that if we let Kp be a fixed field of Gp and then choose a generator of Z mod Pz, so we get a non-canonical isomorphism between Z mod Pz and the pth root of unity, we have the following identification. And then recall that this is just the p-torsion part of the Brauer group of Kp. By the way, this is where we use the hypothesis that the characteristic of K is prime to P, because we had this isomorphism only under that condition. Remember that this was proven by using the long exact sequence of cohomology associated to the short exact sequence of the pth power map. This group of pth root of unity is just viewed as the kernel of the pth power map. But now coming back, now we have reduced the problem to proving that this p-torsion part of this Brauer group is 0. So this is getting closer and closer to our hypothesis, but our hypothesis involved the relative Brauer group, whereas this is an absolute Brauer group. So we wanted to bring it, to relate it to a relative Brauer group. So to relate this to a relative Brauer group, we take some finite extension of Kp contains in the separable closure of K. Then remember previously, via the inflation restriction sequence, we know that we have this exact sequence. In particular, we only care about this part. So we know that this Brauer group injects into this Brauer group. So we can just write this Brauer group, the Brauer group of Kp, as a union of the relative Brauer groups over these finite extension. Thus, if we can prove that the p-torsion part of this Brauer group is 0, then we have that the p-torsion of this Brauer group is 0. Thus now we have reduced this to the relative case. Now this looks closer and closer to our hypothesis. The only obstruction now is that this group in the hypothesis is cyclic of order P, whereas this group is not. Now what do we know about this group? Well, this Galois group is a quotient of this Galois group, which was GP because that was how we define this KP. KP was the fixed field of GP, and remember GP is the Silo Pro P part of the absolute Galois group. So what we know is that this group must be a P power, and that's all we're gonna need. Even though our group here is not a cyclic group of degree P, it's not Z mod PZ, we can relate it to Z mod PZ in the following way. Because this is a finite P group, it is solvable, so we can write a chain. We will have a chain like this, where here the quotients of the consecutive terms are isomorphic to Z mod PZ. And then voila, here, if we look at the Galois correspondence via the Brauer correspondence, this will correspond to a sequence of sub-extensions, right, of K over Kp, and the Galois group of any consecutive here extension is going to be Z mod Pz, so we can use the hypothesis. So from the hypothesis, we now have that the Brauer group of Ki plus 1 over Ki of this, the relative Brauer group, this extension, is 0. So this is very promising. Now we just need to get from here to here. So somehow we need to be able to relate these Brauer groups. So what we have is that we have the P torsion part of this Brauer group is 0, and we want to show that the P torsion part of this Brauer group is 0. So we want to patch this together. Right? And the idea is to use the following exact sequence. So we can restrict that to the P torsion part, and then we have that this is 0, right? So we can use some induction. Then if this is 0, we will have this must be 0, and so we can patch all of this until we get the Brauer group, the P torsion part of the Brauer group of K over Kp is 0. So how do we have this exact sequence? Well, here we use the following proposition. This again is the inflation restriction sequence. Here we apply this for the case when A is Ki star. Now, why do these satisfy the hypothesis? How do we know that the H1 cohomology of these are gonna vanish? Well, that's just by Hilbert 90. Because these are just Galois groups of extensions of degree P, cyclic extension of degree P. That's another way where we use this cyclic hypothesis. Alright, so using induction and this sequence, we can show that we can use the fact that these Brauer groups are 0 to prove that the P torsion part of this Brauer group is 0. Since the absolute Brauer group of Kp is just a union of these relative Brauer group, we have that the P torsion part of this absolute Brauer group must also be 0, but via this we know that this is equal to this cohomology, so we know that this cohomology group is 0. Now that means from our previous result on Pro P group, that actually means the cohomological dimension of this group, the P cohomological dimension of this group GP is less than or equal to 1. But we also have shown that the cohomological dimension, the P cohomological dimension of K is equal to this P cohomological dimension of GP, because GP is defined to be the Pro P subgroup of K. So then we see that the P cohomological dimension of K is less than or equal to 1. Thus we are done. And so remember the key idea there, the key way we use this hypothesis that this norm is surjective is by this description of the norm in terms of the Brauer group.